Okay, so we're given the function f of x equals 2x squared over x squared minus 1. And in part A, we're asked to find the coordinates of the local maximum and minimum points of the function if they exist. So it may have a max, it may have a min, it might have neither, it might have both. Just one thing to note here, when it says coordinates, remember that your answer should involve both the x and the y coordinates. Okay, so A, in order to determine the max or the min, we want to find places to begin with where the tangent line is horizontal. Now, the slope of the tangent line is 0 when the derivative is equal to 0, so we want places where the derivative is 0. So we find f prime of x to begin with, and in order to do so, we'll use the quotient rule u over v. So we have v du dx, so the derivative of u, which is 4x, minus u, which is 2x squared, times dv dx, the derivative of the denominator, which is 2x, all over v to be squared, which is x squared minus 1 all squared. And that formula for the quotient rule is in your log tables, and just it is important to pull out what is u and what is v. And maybe to take a moment to say du dx is 4x and dv dx is 2x. And that's what you use below here. Now let's tidy this up. We want to know when this is equal to 0. Well, let's group terms. So multiplying out the numerator, we get 4x cubed minus 4x minus 2 2's are 4, x squared times x is x cubed. So we add our powers with the same base of x. All over x squared minus 1 all squared. Okay, in the numerator there, we see our 4x's, x cubes will cancel. So we end up with minus 4x all over x squared minus 1 to be squared. Now remember, we want to find places where the tangent line is horizontal, i.e. the derivative at that point is equal to 0. So step 1 was to find the derivative. And then step 2, and I'll write these all at the end, is to solve when the derivative is equal to 0. So that occurs when minus 4x over x squared minus 1 to be squared is equal to 0. We see an equation like this, and you think, well, what don't I like about this equation? What would make life easier? The denominator. If we got rid of the denominator, that would make life easier. So we multiply both sides by the denominator, and in which case we get minus 4x equals 0 times our denominator, but we know that doesn't matter because 0 times anything will give us 0. So we have minus 4x equal to 0, so therefore x is equal to 0. So at x equals 0, we have a horizontal tangent line. Now, we need to determine whether that is a max or a min or neither. So you could have just a horizontal tangent line where the curve kind of pauses for a moment. So in order to determine, we use the second derivative test. So the second derivative involves taking the second derivative, plugging in this value and determining whether you get a positive or negative answer. So for the second derivative, we have f double prime of x equal to, once again, the quotient rule. So here is your first derivative. So we're going to use this to find the second derivative. So we've v, which is the denominator, times du dx, the derivative of the numerator, minus u, which is minus 4x, that's the numerator, times the derivative of the denominator. So we have here x squared minus 1 to the power of 2. The power rule involves multiplying by the power, writing your bracket, dropping the power by 1 and differentiating inside the bracket. Sorry, it's messy. All over the denominator to be squared. So there's our denominator and we need to square it. Okay, so our second derivative, to tidy up somewhat, we have minus 4 times x squared minus 1 to be squared. And then multiplying through here, we have x squared minus 1, we have 2x times 2, that gives us 4x times 4x gives us 16x squared. Minus and minus will give us a plus. So we have plus the 2 and the 4 giving us 16, x times x is x squared, and we have x squared minus 1. All over x squared minus 1. Now the square to be squared, we multiply the powers. There are those nested powers. A to the power of b, all to the power of c is a to the b times c. So we end up with a power of, sorry about that, we end up with a power of 4 in the denominator. Tidying up a little more, so we have f double prime of x. We see here that the x squared minus 1 term is common to both. I'm going to factor it out. So you have x squared minus 1 times minus 4 times x squared minus 1, what remains from the first term, plus 16x squared. all over x squared minus 1 to the power of 4. Tidying once again, we have the second derivative equal to, now we have x squared minus 1 above, x squared minus 1 to the power of 4 below. We can cancel the one above with one of the ones below. So we end up with x squared minus 1 all cubed. And inside the bracket we have minus 4x squared plus 4 plus 16x squared, which is 12x squared plus 4 all over x squared minus 1 to be cubed. There's our second derivative. Now I have tidied it up a bit because we're going to need to know about inflection points, so we're going to need a nice form of it in a moment. But what our aim here is to determine whether at x equals 0, where there's a horizontal tangent line, is there a max or a min? So we plug that value into the second derivative and we get 4 over minus 1 cubed, which is minus 4. In particular, it's less than 0. If the second derivative is less than 0 at the point and there's a horizontal tangent at the point, we know by the second derivative test that there is a local max at x, the point when x is equal to not 4 but 0. Okay, being less than 0 indicates that there's a local max. So we have a local max at the point when x is 0. Now when x is 0, we need to determine the y value. And the y value when x is 0 is given by subbing back into the original function. Bear in mind, now we're looking for a point along the curve. And don't forget, you need to, for the y coordinate of a point on the curve, we sub back into the original function 2x squared over x squared minus 1. So f of x is 2x squared over x squared minus 1. And the f of 0 is 0 over minus 1, which is 0. Okay, so these are the coordinates of the local max. The local maximum point, and there is no local minimum point. Okay, now there was a second part to this question that said, show there are no inflection points. An inflection point occurs when the second derivative is equal to 0 and it changes sign. So for part B, inflection points, you want to solve where f double prime of x is equal to 0. Now we have f double prime of x. It's equal to, we have it up here, 12x squared plus 4 over x squared minus 1 to be cubed. When that is equal to 0, well, when does that happen? We have a denominator, we'd like to get rid of the denominator in order to solve, so we multiply across by the denominator to get 12x squared plus 4, and the denominator over here times 0 is 0. So we have 12x squared equals minus 4, so x squared is equal to minus 4 over 12, which is minus 1/3. But this is not possible because when you square a number, it's always going to be positive. So not possible. Therefore, no inflection points. Okay, so just in summary, when to find max and min, just a few steps. Step 1, find the derivative, dy dx, or f prime of x. Step 2, solve when the derivative is equal to 0. That tells us the points where there is a horizontal tangent line, okay, which could look like any of the above. And then step 3, use the second derivative test on the points that you found in points from step 2. So that's for max and min, and very similar approach and steps for finding points of inflection. And we'll just keep an eye on the steps above as we do this. So step 1, for points of inflection, we want to find the second derivative, d2y dx squared. Step 2 is to solve that equal to 0. And then step 3, which is like the first derivative test, which we didn't use in this problem, is check that d2y dx squared changes sign at the points you found in step 2. Okay, so when you see the parallels, it's a very similar analysis, but in the first case, we're looking for maxes and mins. You find the first derivative, you solve the first derivative equal to 0, use the second derivative test. Points of inflection, find the second derivative, solve the second derivative equal to 0, and check that it changes sign at the points from step 2. The point of inflection is where the curviness, let's say, changes. So it changes from being, this would be concave up, this would be concave down.